All right, welcome back. Another week. Here we are, ready to do some Bayesian psychometric modeling. Today's a great day. We're talking psychometrics. Actually, very little Bayes, although I'll find a way to put Bayes in what we're doing as well. I have two announcements for today. Number one, just a reminder, formative assessments are due every Monday by 11:59. So they're not. If you miss them, you don't get to redo them. So there's another formative assessment 2 is out. Just posted it just a moment ago, and so please take a look at it. It will not take you very long to go over what we need to talk about in that formative assessment. And again, I use that to figure out what I need to slow down with. Normally, as we go forward into the semester, this time Vladimir will lead us through sort of the answers to the formative assessment to sort of talk about that. But because the first formative assessment was just about office hours and class setup, I think, Vladimir, we both decided that's probably not a good use of our time today. Is that right? Okay, he's smiling, so I'll take that as a yes. It's just something that, I'd like to make sure that we don't miss as we go forward. Next thing to talk about is homework number 1 is due Thursday. It is basically get Stan running on your local machine and make sure Stan can run on the notebook side. So that is point number 2. So that's, I would tell you right now, start it now if you haven't already, because it will be, if Stan doesn't install, it'll be a long time to get it. It'll take some time to get it to install. You could be like me or like a lot of people and be like, hey, it installed first time. Let's hope that happens. But in the early days of Stan, it was never that easy. So hopefully this has gotten better for everything. All right. Anybody have questions for me before we begin? Anything about last time? Anything about class? Anything about homework? No. Anything about my life choices? Probably not either. Do you remember last time? I mean, it was a 3-day weekend ago. Labor Day happened. So if I were to ask you things like, what's a prior distribution? How would you answer that? Don't all jump in at once. I'll wait. I would nitpick a bit of it because that's my job. But the prior distribution is placed on a model parameter, and the model should talk about the data. So you mentioned the prior. You said assumptions about data and prior. I was just nitpicking that for just a bit. Mostly correct though. Yes, a prior distribution represents our belief about what a parameter should, where a parameter is likely to be in like a numeric sense. Right. And last time we saw a beta distribution for a prior, we compared an informative and an uninformative beta distribution, right? Informative being there was a big peak right around where we thought 1/6 chance of a die roll should be, whereas uninformative had sort of spread that out. That was our. All right, another question for you. What's a conjugate prior? I got to lean into the silence. Just Ryan. That's right. A conjugate prior, pretty close. I mean, again, I'm going to nitpick because that's just my job. All right. Ask my advisees, my one advisee in this class, and he'll tell you that's what I do, right? Especially if I send me written work. But that being said, a conjugate prior is a prior where the distribution of the prior, the family of distribution, so in our case from the last example, beta distribution, was the same as the distribution of the posterior. So beta prior, beta, and then a binomial was the data model, led to a beta posterior. Now the actual parameters of the prior distribution are not the same, right? Because you update the prior when you a posterior is sort of your updated belief, right? We saw that last time. We could update what we believed the likelihood of rolling a 1 on a die would be. I'm just putting this out to remind us about this a little bit. There's one other version of a prior that we'll sort of talk about a little bit today, and I don't think I talked about it last time. But before I ask that question, let me ask one other question to you from last time. What are hyperparameters? Of which distribution? There you go. Prior distribution parameters are hyperparameters. Thank you, Erica. Thank you. Sorry, not to, again, I have to nitpick. Again, not a knock on any of you. It's just a personal failing. But the prior distribution's parameters, and last time we saw beta had this A and B parameter or alpha and beta parameter. Those parameters themselves are hyperparameters. Last time we set them based on our belief about what the prior should look like, and we sort of played around with the shape, or at least my slides kind of compared a couple different shapes for it. Today, in psychometric models, tying just regular psychometric models to Bayes, I'm going to talk about another version of prior distribution, which is a prior distribution where we estimate some or all of the parameters themselves. And that is what we call an empirical prior distribution. So for instance, you may have been, I mentioned last time, a random intercept model where you've got a random intercept that follows a normal distribution, what has a fixed mean of 0. The mean is a hyperparameter that's fixed at 0, but the variance may be estimated, right? The random intercept variance. That's a hyperparameter, but it's estimated. So what the term we'd use for that is an empirical prior distribution, meaning we let the data sort of pick the hyperparameters and how we build things. All right. That sound good? Everybody remember that stuff? All right. Any other questions about that before we dive into not that for now? In the absence of questions, I'll move forward. Okay, once again, on our class notebook site, you can find Lecture 2, have a PDF there. The HTML slides are what I'm going to work with today. And because most of today doesn't involve R, I'm just going to show these slides to you in terms of just a regular presentation like this. But I may flip back and forth depending on how this goes. So today, literally, we're just talking psychometric models. And I say just. This is like all of the psychometric models, the way I'm trying to put it. So you may take a class on structural equation modeling and factor analysis, where the predominant model you hear there is factor analysis, confirmatory factor model. Tied to that, you get into a little bit more of the generalized traits. If you take it from Lisa Hoffman, it's a generalized class. That is sort of the framework I built as well that I like to think about. But then comparatively, in our program, we'll have item response theory as a class. That's a latent variable model. Let's think here. G-theory is a class. Turns out that's sort of a latent variable model. It's a random effects model as well. And if I really wanted to lump this together, I'd throw multi-level models, the clustered or the longitudinal type in here, because those random intercepts function like latent variables as well too, believe it or not. So from this, when I say just psychometric models, this is like all of the psychometric models. This is years of coursework put into one little lecture, and it's just the basics of it. So that means two things. Number one, I'm using this to frame the discussion. I'd like you to hear them in the language that I speak about them in. That way you can understand when I talk about certain features. My language tries to be consistent with what's in the field, but I have my own version of way of talking about things, right? It just happens. Second, it gives us a bit of sense for like where the scope is and where we're going to start really applying our Bayesian methods and how we estimate these models. And there's a few catches in psychometrics that make Bayesian methods not just as easy to apply off the shelf. But third, that means we're not really going to go in depth into each of these, right? Because we have courses that cover a lot of the detail, a lot more in depth with each of the modeling methods. This class will be a lot about, here's a model, here's the nuances that we need to think about when we estimate it, and here's how to estimate it as well. So toward the end of the class, it'll sound like we're throwing models together left and right, but today is sort of our framing for it. So if you need more information about psychometric models, don't hesitate to let me know. I will also note today's lecture has 2 readings, 2 chapters. They're very introductory. I put them on Icon. They're from Rod McDonald's 1999 book. Roderick McDonald was the first person I had a class with in grad school. I was really lucky to have him as a professor. He was very influential in my thinking about latent variable models, and so those chapters are sort of what we are going to sort of help frame my knowledge of what we're talking about today. All right, here we go. Let's think about this. Take a look at the following items from McDonald's book from the satisfaction with life scale. This is a live survey that I created on our Qualtrics site, and hope you can see that. Questions are, I am satisfied with my life. You know what? I think I'll somewhat agree with that today. I'll just give you my head here. The conditions of my life are excellent. Yeah, I'll strongly agree with that. I'm pretty lucky. In most ways, my life is close to the ideal. Well, I'll somewhat agree with that. Maybe not perfectly, but that happens. So far, I've gotten the important things I want from life. Yeah, definitely. And if I could live my life over, I would change almost nothing. No, I can't say that. I've changed a lot. But there you go. Satisfaction with life scale. Have you seen this before? Probably have. The guy who was really well known about this, his name was Ed Diener. His office was literally across the hall from my grad student office in grad school. Also, he was on Time magazine back in the 90s. It was like, oh, that's kind of cool. But thinking about it from a measurement perspective, this sort of frames the discussion. Here are 5 questions we asked people, each with a set of options they had to pick to indicate how much they agreed or disagreed with the question itself. This is fairly standard, right? In fact, we might call this a Likert type scale, right? Although technically, Likert's dissertation showed that a very complicated scaling method resulted in just about the same amount as integer scoring for each of these. So oftentimes we just add 1, 2, 3, 4, 5 is what we give, and we analyze those data. But now, I'm not talking to you about that because of happiness. Believe me, I am the last person who can tell you about what to do to be happy. But I am talking about this from the perspective of the analyst. If you're sitting there and your friend, your lab mate, your colleague says, hey, I have these data. How do I analyze it? What do I do? This is the first question I'd like to ask you, is a discussion question. How would we analyze these types of data? Or better yet, I'm going to ask the 2 questions because they sort of fit together. Do you know of any psychometric model that might work for these data? So I'll just open it up. Let's have a little bit of discussion. Anybody want to jump in? How would you look at this to analyze it? Like, what would you try to do? What's a research question that you might ask, and how would you answer it? By the way, that research question thing, for those of you who go through the comps or dissertation process where you're doing projects and stuff, critically important to define that first. So maybe I should have defined it. My research question is this. How accurately am I measuring one construct with these questions? Satisfaction with life. So, what would you do? What type of model would you use? What type of analysis would you do? I'll whistle. Anybody? Would you assign a number to each of those categories and then add them up? I saw a yes assigning a number. Let's talk about that. Let's imagine I ordered them strongly disagree as a 1, somewhat disagree as a 2, then 3, 4, and 5, right? Okay, now we've put them sort of in a numeric sense. What do? Do we add them up? Well, I mean, that's what they do in, medicine or psychology. Why can't we add them up? May not equal contributing. Actually, adding them up makes some very strong assumptions. Absolutely. All right. So what do we do instead? I'll wait. I mean, I get paid. I get paid either way if I'm talking or not. Either way, it happens. Yeah. So the options themselves, let me try to reword what you said. Good point. The options you're saying are, when I number them 1, 2, 3, 4, 5, they really don't reflect a 1 unit difference between. And really what we should be considering in any type of modeling approach is the relative distance, or sort of ordinal categories. We know that a person who selects somewhat disagree has a bit more agreement to the item than someone who picked strongly disagree. That's a bad way of putting it, right? But anybody who picks a higher option endorses the item more, but maybe we don't know exactly how much more. Is that what you were saying? I'm supposed to have that language to have this class, yes. All right, that sounds good. Okay, so that, Sergio, describes a type of way of looking at the data itself, the numeric entity. What about the modeling perspective? What type of model on the right? So if you think of data as the left-hand side of the equation, on the right-hand side, what's the model? Go ahead, Ryan. Could do some type of regression scoring. Yep. How well do they correlate with an overall construct? Getting there. Let's take that construct. A comment in the chat. IRT. All right, so frame it out for me. What is IRT different? What does IRT have in it? What's the construct represented by? Going back to what Ryan just said. So let's think about the process of measurement, right? A latent trait. There we go. Perfect, Ryan. The idea is we're mapping people's behavior, in this case, people's selection of different choices, onto a numeric continuum that we can't observe. That's the goal, right? Here, what we're saying is there's this underlying construct called satisfaction with life. We're not only going to measure it with these items, we're going to then map those items onto a continuum to talk about who has more or less satisfaction of life, but also look at how well those items may describe satisfaction with life overall. How does that sound? So far, so good? So IRT is one approach, item response theory. Item response theory you often find in, at least in our program, we teach it in the context of educational measurement, but item response theory is broad. In fact, all these methods none of them were started in education. Even if you're in education, IRT actually came not from education, believe it or not. Depending on who you define first, but Fred Lord, in 1950, he had his monograph of his dissertation. He was a psychology student. Turns out E.F. Lindquist here in our program worked in the psych department, had a psych degree as well too. So the point I'm trying to make is none of these are owned by anything. And you may think of IRT, we think of that latent trait often as ability, but it doesn't have to be. I once taught item response theory at Michigan to a group of political scientists. Why? Because they were trying to figure out political ideology as a latent trait. And you may have voting members of Congress voting on bills. And so bills are items, and how people voted, yes or no, was a response. And so you can put people and bills on a continuum as well too, or multiple continua. But yes, so let's think about it. Now we have a latent variable that we're envisioning. Item response theory is one way. Item response theory implies the use of discrete distributions for the items. So that might work with what Sergio was talking about for worrying about these items discretely. I will say in most of the world, though, when you talk about satisfaction of life, they'll take that numeric scale, 1, 2, 3, 4, 5, and use a factor analysis for it. Now, factor analysis and IRT are very similar. and that we have a continuous latent variable that if we could observe, we could go and then use to predict the response, the probability of a response for each of these items. In factor analysis, we're using a straight linear regression approach to what we do. So, does this bring back memories of stuff for some of you? All right. Turns out, when I said, why don't we just add these up? 1, 2, 3, 4, 5. Several of you were in my class I taught last fall about multidimensional measurement models. That approach has a very specific name to it. You may remember. It's called the parallel items model, which is a confirmatory factor model where each loading is equal to each other and each unique variance is equal to each other. Right? So, turns out adding things up is a testable model as well too. Okay, moving forward. Let's talk a little bit differently about this, though, and this is sort of the interest for today. Here is those same 5 items, but I've changed things just a little bit. I'm satisfied with my life. 1, 2, 3, 4, 5. That's the same. The conditions of my life are excellent. Yes or no? In most ways, my life is close to the ideal. This is disagree. This is strongly agree. Slider bar. In the past week, now this is a different item. In the past week, I've thought of how happy I felt how many times. I don't know. How often do you think that? Don't know. Or if I could live my life over, I would change and an open-ended response. So now I've changed the format of the item. This one is a little bit a different item overall. But now let's imagine you still intend to measure satisfaction with life. You believe it's one continuum, one latent trait that measures it. What do you do now? How do you analyze these data? Can you? Am I not asking the right question? That's usually my problem. I ask terrible questions. Can you take, let me ask a different way. Can you take, let's imagine that we all agree, even if you didn't agree, that last time, on the last slide, said we should use some type of IRT model for this. Can we still use some type of IRT model for this? Yes. Sergio, do you have a thought? Yeah, this slider bar here. Yeah, it's sort of a truncated. So the answer was yes. Now that's I have to admit I asked a loaded question, because if you ask me what item response theory means, you have to actually define it. And what we define item response theory in educational measurement as is latent variable models with discrete outcomes, generally speaking. All right. Whereas if it's a continuous outcome, we often say, well, that's not IRT, that's confirmatory factor analysis, when really it's half 6 of one, half does the other. Often when you're in a testing paradigm or when you're in a classroom, you have a bunch of items that all have the same type of format, right? Last time on the last set of these slides, we had 5 option Likert type items. They were all the same. That means every item's model is the same. But here I've got 5 options here, and if I were to use some type of IRT model, maybe I'd say the graded response model, which we'll define later, to describe this, would I then not be able to take another item and use a binary item response theory model with that in the same model? Is that allowed? What do you think? I should note, part of the problem that I'm talking about here is the verbal definition of IRT, not the mathematics. Ryan, yes. That's a great answer. Yes, you could model it, the items themselves will have different distributions. And the fact that you said the D word, distribution, in class is perfect, because guess what? That now becomes part of, remember Bayes' theorem, we've got the prior distribution, which goes to our parameters, and we've got the model data likelihood. What we're talking about here is the model data likelihood for each of the items, and how we combine those together into a joint likelihood for all the items at once. And the answer is yes, you're right. The first 5 items might be modeled with a categorical distribution. A categorical distribution is effectively a one-trial multinomial, which means there's a probability associated with the selecting each of these. Those probabilities sum to 1, and technically it would be conditional upon the value of a person's latent trait. So if we could observe their theta, we could predict which probability they would the probability that would select each of these options for. Well, it turns out the next item is a binary, a two-choice, right? Which is still discrete, still categorical, and it's the lower endpoint of the categorical distribution, which we would just call a binary or Bernoulli distribution for these, which is very similar to us rolling the die the last time. Now, this slider bar is a little bit more interesting. In theory, there's infinite precision. In practice, it's somewhat, it looks like there's, in this case, 101 integers from 0 to 100, right? There's probably too many integers to take a binary modeling approach. We may be able to approximate this with a continuum, but that continuum, almost like a normal distribution, like a factorial model would do. But there's a slight problem in that if we have a lot of people who end up using the extremes, which I don't know about you, but I take surveys in the extreme always. Like, just get out of here, right? Actually, I don't take surveys anymore. But yes, you know what I'm talking about, right? Those extreme responders, they will be up against the bounds, and a normal distribution goes to infinity in either direction. So we need to truncate it somehow. And there are multiple ways looking at that. One of my advisees, one of your colleagues, Alfonso Martinez, assistant professor at Fordham, has some research where he's talking about using a beta distribution for the middle part, but then having it basically have a probability part for the upper and lower bound as well. So it's like a 3-part beta distribution that puts into it, which would also fit. This one right here, how many times is a count? A count variable we use, there's a bunch of discrete distributions. Remember, a count is bounded below by 0, uses integer values, so discrete values, and may not have an upper bound functionally, although I can't imagine someone saying I thought infinitely about my happiness, but that's the sort of the distribution that we're dealing with. Names of count distributions, or distributions that we use on count, include Poisson, negative binomial. Sometimes you will hear zero inflated Poisson, or a hurdle model sometimes. A zero inflated negative binomial. These are different models for counts. And the reason why there's so many is that not every one of them, each of them has a certain assumption about, for instance, how the mean and variance are equal. A Poisson distribution, the mean and the variance are equal. But if you have more variance than you have mean, it's called over-dispersion. So you get into cases where you have to change the model a little bit as well, too. So the same thing goes with the negative binomial and the zero-inflated versions of those as well, too. And finally, this last one, open-ended text. How on earth do you use that? Well, it turns out there are such things that look at text processing for themes and language. Now, this is probably too small of an item to really build with, but we could actually do something called a topic model to group the topics that people talk about for what they'd change their life in. And that topic model would be sort of the item response. But then that topic model could indicate a person's happiness or subjective well-being, satisfaction with life, by describing a person who is a certain level of happiness tends to write about things like this that they would change in their life, versus a lower level of happiness may change different things in their life, right? So it all can be built together. It's still a latent variable model. It doesn't go by a name, but it's all possible. And the key to it all is the idea that your data follow some type of distribution, and you have to map that distribution onto your data. We literally do that in our classes by topic area, right? Factor analysis, we assume continuity, and then when Lisa teaches it, she added some of the generalized stuff that involves categorical distributions. In item response, we start with the opposite. We start with Bernoulli or binary data, add in some of the categorical distribution as well. So we sort of took that guesswork out of you in the curriculum. The point I'm trying to make is math don't care, right? If you define a latent variable and you collect data under a certain format, the key in modeling it is picking the right distribution for the data and mapping the latent variable onto that distribution. How are we doing with this so far? Now, this is the idea of generalized psychometric models. So when I talk about latent traits, our framing example, that really is what I'm talking about. Okay, questions? Okay, discussion over. By the way, I'm terrible at discussion. I know it. I'm sorry. It happens. But let's just... I have to try, right? Do you like the discussion? I don't know. Yeah? Okay. All right, let's think about latent traits from a big picture view, right? Thank you, James. Latent trait theory posits there are attributes of a person typically that are unobservable, which we call latent, quantifiable, right? And related to tasks that can be observed. These are sort of the premises of what we would call back in the 1950s, 60s, 70s, and still a little bit today, there's a group of people talking about the philosophical underpinnings of measurement. Sometimes we call this axiomatic measurement, right? Where sort of defined the conditions on which we can map behavior, in our case, answering survey questions, to a continuum that we don't observe. Often these attributes are often called constructs. Hey, Templin, way to go. Often. So these attributes about the person that we're trying to measure are called constructs, which underscores to me that they are constructed, but because they don't exist. They're not directly observable, right? So each of these topics can include a general or a specific ability. For instance, in education, the ability for a person to do third grade level mathematics is a version of a construct. Similarly, in that same vein, the ability of a person to do standard 3 NVT1, right, numbers in base 10-1, which is an educational standard taught in the third grade, could also be a construct. It's at a different level, but it's still an unobserved measurable construct itself, right? So just because we may build tests that are called mathematics doesn't mean we have to. We literally have defined that as our term, okay? Second, these could be a feature of personality, right? Previous example, Ed Diener, I believe, worked in the social and personality program when I was in Illinois. I would call that personality psychology, satisfaction with life, subjective well-being, whichever you call that. Extroversion's another one. Think of all the inventories you've heard. MMPI, Minnesota Multiphasic Personality Inventory, the Beck Depression Inventory. Go down the list. All those. Same thing, right? A person makes an assumption about what the trait sounds like, right? What it should be. Depression, extroversion, creates a set of tasks or items that they are going to have subjects respond to or perform, and then uses a model to derive an estimate of where a person's latent variable score might be itself. So, but regardless of domain, regardless of the constructs you're measuring, the psychometric models are the same. So whether you're using it in psychology, whether you're using it in education, I will give you a quick story. I give you all sorts of stories. This one's trying to be quick. Another one. I had a couple interesting phone calls this summer with a Major League Baseball team that will go unnamed, although I'm not under non-disclosure, including a phone call where, there was the president of baseball operations on, an assistant GM, somebody who won a World Series, these types of things. Anyway, they said to me, "Hey, look, we have a bunch of ways of measuring things really accurately, like swing speed or visual acuity and so forth, right? So just because we can measure those accurately, it doesn't help us understand whether a person makes a good decision about swinging at a pitch. How do we put them together to do that? Yet another domain, baseball, right? But we could potentially build a latent variable model to describe it as well too. So latent variable models, if you're a student of this program, you will only hear about them usually in education and usually very narrowly defined, but they're everywhere and they're wide. And like I mentioned before, did you ever think, I don't know if you've seen it, but some of the cool work about IRT and political science, go look that up. It's pretty neat to see as well too, right? But we're not talking items and people. We're talking Congress people and bills. Actually, people have done the same for the Supreme Court, I believe, as well too. So interesting stuff. So that's why I like to say math don't care. Really, the mathematical model is agnostic. It doesn't matter to the math whether you're putting in educational ability or the ability to swing a baseball bat, right? The math is the same. The difference is the context. Right? The difference is literally the math is the same, the models are the same. So what you learn in this class will be the same. How you describe it, who your audience is, will be different. All right, who's ready for an exciting history? Long history. You know, that's a bad slide. I shouldn't do that. That usually means, it's like when someone starts a meeting saying, hey, I think we're going to get out of here early. You know what that means? It's not going to be early. A long history is like, get ready, take a nap, right? But we'll just go quick. Latent trait theory, as we now know it, started ages ago, before most academic disciplines did, right? You can look back through history, recorded history, and people will talk about tests, educational assessments, we can call that, centuries ago. Multiple continents, Europe, Asia, you name it. It happens, right? They still sought to measure latent abilities. Our modern version of this really started in the mid-1800s with the study of intelligence being a latent trait. And I won't give the... Francis Galton was a big name in it. Recruited Pearson, led to Spearman, yada, 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 and go on to our time now. But methodological innovations have often spurred empirical trait development. So this is very interesting to me, right? So in the beginning of what we call modern trait theory, we were after basically measures of intelligence. And the story, as I've read it and heard about it, was 1850s, 1860s, Francis Galton sought to measure intelligence, and they started doing so using questionnaires. Like there was a story I read once about having people who attended a World's Fair fill out intelligence questionnaires. What? Anyway, right? So intelligence was just a thing. Hey, I'm going to measure your intelligence. It's one construct, right? In 1904, Spearman ended up with two papers that sort of led to different branches of what we did. But again, it was just one construct. By the 1930s, people were asking, is intelligence really one construct, or is there multiple dimensions of intelligence? And so multidimensional factor analysis started to come about, which then brought about multidimensional constructs, such as in intelligence being one of them, but also in personality theory. Right? So what you end up seeing is this sort of interchange between methodology and what we're measuring. Shortly after the 1930s, 1940s, 1950s, item response theory started being talked about, 1960s certainly, and that changed how we build assessments as well too. Multidimensional item response theory exists, multidimensional models as well. So all these types of methods that we've developed have often turned about to help us really go and measure constructs more accurately, in a more nuanced way that may matter a little bit differently. So that's my point in trying to say the history of it. The other part of it is early methods were also limited by mathematical and statistical theory. So I don't talk about exploratory factor analysis in this class. I probably could. But the reason for it was exploratory factor analysis was the only method we had up until the 1960s to study what we do with measurement. Right? That was the only. Have you heard the saying, if all you have is a hammer, all you see will be nails, right? This is it for exploratory factor analysis. Bang, bang, bang on those nails. So where things radically changed was in 1967, the maximum likelihood factor analysis paper with Joreskog allowed us to estimate factor models with a very well-known structure, conformatory structure, which led to CFA. Right? That changed radically how we do measurement. In fact, so much so that another one of my academic heroes, a guy by the name of Michael Brown, conjectured that we stopped doing research in exploratory factor analysis right about the time that Joreskog's work came out. So you don't see newer versions of rotation methods or things like that because of it. So long point of this is that to measure things well, we need a good toolbox. And we didn't always have that toolbox, whether we were constrained by theory, statistical theory, or computing applications, like up until the 1960s. Actually, even today, the invention and widespread use of computers, actually getting to that, really made psychometrics possible. That's where we're at today. Trying to do what we're doing in our class without a computer, forget it. We wouldn't happen. And so computers happened, and then better Bayesian methods came along as well too. So the same process. We have these tools that we do science by, and the iteration between better science and better tools sort of is an interplay. All right. Questions on that? I feel like I'm like scrambling. I shouldn't. Take a deep breath, Jonathan. No more caffeine. All right. Okay. So the other thing I'll mention is latent traits are interdisciplinary. Right? So just because we are teaching this class in a college of education, and there happens to be a large assessment or testing industry where a lot of our students end up getting jobs, don't forget, even if you're one of those people who gets a job measuring students in schools or measuring applicants, test takers to become nurses or in licensure or whatever it is, just remember, almost every discipline has a version of latent traits. Meaning, and in each of those disciplines, we may end up having similar methods that were also developed separately. So while in education, Fred Lord's 1950 monograph started the two-parameter normal ogive IRT model, or Rosh's 1960 Rosh paper, or 1967 Birnbaum in the Lord and Novick book, 2PL. Over in psychology, after Euroskog, we were getting into item factor analysis. Right? Turns out both of these are the same mathematical model, but the branches of where they were developed diverged right after the 1960s. And in psychology, we focused on estimating multiple dimensions in item factor analysis. Whereas in item response theory, we stopped really looking. I mean, there's MERT, certainly multidimensional IRT has been around a long time, but it took a back seat to it. And so what that brought about was a lot of our educational tests have one trait, so we sought to understand how to measure that better. Whereas in psychology with many traits, we need a better estimator. Maximum likelihood, marginal maximum likelihood, is nearly impossible in multidimensional item response theory or item factor analysis. So my argument is item factor analysis, really the big difference between it and IRT is in item factor analysis, there were researchers who developed a method called what we call now limited information methods. The things that are behind Levon or M+'s default options for categorical data show up. Whereas in education, we got better at understanding the impact of each item on measuring a trait, or how we define bias or diff and so forth. So many different terms for the same ideas, right? Such as the label given to a latent trait. And so when I co-authored a book about diagnostic models, came out in 2010, a long time ago now. In writing that book, we were trying to make it interdisciplinary. And honestly, the thing that held us up was, what do we call the thing we're measuring? Is it a factor? Is it an ability? Is it an attribute? Is it a construct? Right? Who knows? But those are all synonyms. Those all mean the same things. Right? Some of your fields may call it ability. Others may call it a factor. The other thing that was actually the bigger flip to us was, what do we call the person giving you the data? Sounds trivial. I kid you not. We landed on respondent because it was somewhat neutral. But what we would call examinee here in education, we might call a participant or a subject in other fields, or a patient in medicine, a student, in a particular context. So what this means is the following. There are a ton of words. There are a ton of words. Ton of synonyms, and I'm not even going to be able to cover all of them. But generally speaking, the words that you will hear me say will be related to many of the words that you know about when it comes to measuring this work as well too. Okay? And we're going to focus on the concepts themselves. And by the concepts, that means we're going to define, this is where equations become absolutely important, right? Because if you have a survey that looks like this, you can say, I ran an IRT model on it, and someone's going to say, you can't run an IRT model on continuous data. Okay, well, what's the name of my model? It's a latent trait model, basically, a generalized latent variable model. So you start running out of words at some point to describe what you did. Math is unambiguous if done correctly. All right, questions. I love how I led the loaded question there. Questions, and I'm shaking my head no. No, you don't. You don't have questions. I should ask, though. Do you have questions? Gotta get back in the flow of things. When I ask if you have questions, I need to take a drink. And that pauses me to allow the questions to come out. Otherwise, it's any questions? Okay, we're moving on. That's not. All right, let's talk about constructs. To me, the best constructs are built purposefully, right? You can't just take a bunch of, in our case, survey questions or items, throw them onto a form, ask people to answer them, and then go and analyze them and expect to have anything good. A definition of a construct typically includes what the construct means and what observable variable behaviors are likely related to the construct, right? So for what we're going to do in this class, observable behavior will generally mean answering questions on an assessment or a survey. But it doesn't have to be that. Remember, I gave the baseball example earlier, right? Those are behaviors in a baseball field that we're trying to measure, to use as data to measure a latent variable themselves. That is strange if you're only thinking about this in the context of ability, right? So modern psychometric methods are built around specifying the set of observed variables to which a latent variable may relate. In our case, what are the test items themselves, right? And that's why, another reason why I don't go into exploratory analysis very much. Like, back in the 1940s, when all you had was exploratory factor analysis, yes, you'd create a construct, well-intentioned construct, and then go throw it into this analysis machine. Well, it turns out a lot of those exploratory analyses have assumptions that are made that may not give accurate results. To me, the best approach is, if you understand what your construct is when you build it, when you build the questions to measure it, then you don't need an exploratory analysis, because any difference between your construct in the exploratory analysis and the structure of your construct that you believe and what you get from the exploratory analysis may be an artifact of the method that's being used. In exploratory factor analysis, that's absolutely the case. And I can tell you why if you'd like more in detail about it. In fact, if you really would love to see it, I can show it to you in class here. But less detail there. So when I say here, what observable variables are likely related to the construct, we're going to flip that around, right? When I say related, right? So here, answering the question, I am satisfied with my life, is highly related to whether or not a person is happy with life, satisfaction with life, right? By definition, in the title, we would conjecture that would be highly related. We're going to turn that relationship into the term measure, right? And it turns out Bayes' theorem is heavily involved in that as well, too, right? In Bayes' theorem, we had this flip, right? The likelihood of B given A is the likelihood of A given B times the prior likelihood of B, or is proportional to that, right? Here, we're going to see that Bayesian flip well defined, where we say, it's the likelihood someone answers this, the likelihood of a trait given the data is really the likelihood of the data given the trait plus times a prior times the trait itself, right? So that's really where it comes from. Educational assessment items, which we'll probably have the most of in this class just because of who's teaching and where we're teaching this, do measure some type of ability. So our guiding principles. To better understand psychometric methods and theory, I recommend you envision what you would do if latent variables were not latent in the first place. And by what you would do, what I really mean is, how would you build a model if we could directly observe what we cannot right now? Have you ever thought of it that way? Because we have a ton of statistical models. And if you know a little bit about like linear regression, for instance, you could probably use that approach in how we look at things. But beyond that, let's just make an example. Imagine we could directly observe mathematics ability. What would we do with it in a math test, right? Well, if we had 20 items of math, broadly speaking, and we actually could observe a student's math ability, to talk about how well ability related to each question, we would come up with a prediction. Right? It may even be a logistic regression where we take a math ability as a predictor and we have the probability of a correct response for each item as an outcome. That's a logistic regression with 20 different variables. A 20 variable logistic regression, multidimensional logistic regression. Multivariate, pardon me. All right, doesn't that make sense? Psychometric models essentially do this. We take observed variable, we use observed variable methods as if we know the value of the latent variable. So for instance, when I just said logistic regression, if we observe the variable, if we didn't observe the variable, that logistic regression becomes a 2-parameter item response model. Same methodology, we just didn't observe the variable. It's a little bit of a problem, but does that make sense? Right? If we had continuous data and we predicted it with, if we could observe a trait, that would be linear regression, right? Here, I'll give you another one. Diagnostic models, the stuff I work on, have worked on. I don't know if I work on them much now, but, right? They are, when we have binary items, we would say a logistic version of analysis of variance, where the latent variables are crossed, discrete factors. Right? Developed another model for hierarchies that we call attribute hierarchies, where somebody has to learn something first before learning another thing. Turns out that's a nested analysis of variance. Right? So if you know a lot of statistics and a lot of linear models, it turns out the combination of measurement with crazy variables fits perfectly into it. You're already doing that. You've already learned it in your stat classes. We just never talked about it that way. But those statistical models from your stat classes are what we use to do measurement models in psychometrics, with the only caveat being the term that's usually a predictor in the model has not been observed. And I say only because only in our latent variable world would we say that's not a problem. In most places, you'd say, hey, guess what? I got a linear regression design. I'm going to collect Y, and I'm going to model it. Oh, wait, I totally forgot to collect X, though. How do I go and figure that out? Who's going to say that? All right. There are some catches, right? We need data collection designs that allow for such methods to be used, right? We need a formal vetting of whether or not we did a good job measuring the construct. So even though I'm arguing that to think about what we're doing in our class and in psychometrics in general, you should think about the latent variables as being observed, because I think that actually solves a lot of problems. I would argue that in not all cases can we go and do that. The example I just said, hey, I'm going to collect X and Y. I'm going to measure X, I'm going to collect Y, and I'm going to do a linear regression to it. It's not as simple as that. You can't just have one outcome and create a latent variable, right? You have to actually have more than one. You have to 2 or 3, depending on the bare minimum in the construct that you're in. So not only that, when you get into multivariate methods, the idea of model fit is critically important as well, too. And most of our psychometric models are multivariate methods. All right, how am I doing? Is this making sense? Is it philosophical enough to be a PhD course? That's what your degree is really in, right? PhD. One of you already has one, so yes. All right. Measurement, formally defined. Measurement is the quantification of some characteristic, physical or otherwise. Right? Let's imagine the measurement of length, right? A physical construct. But at some point in human history, we didn't call length a physical construct, right? So think of, in your history of math or history of science classes, just measuring the length of something, right? Why would we need to measure an object's length? Well, we need to know what might fit in dark places where we need to put things, right? If you ever need to build something, you need to know how big you're building with. How do we measure it? Well, in our case, we use a device, a ruler, a yardstick, a tape measure, right? And we start at an origin and we note its length itself, right? And then what are we using for distance? Well, turns out that's where subjectivity comes in. You see, here in this country, we're one of the few holdouts that insists on inches, although I understand it's a little bit more complicated than that in many of our English-speaking countries as well, too. But that being said, centimeters, meters, you name it, there's a distance, right? Each of those distances is different, but the construct is still the same. We still need to measure the size of things. And so long as our units are the same, Like if I measure the door in inches and I measure my desk in inches, I can tell whether the desk will fit through the door effectively, right? If I don't measure it in inches, if I have the inches for the door and I have centimeters for the desk, because the construct is the same, you should assume that I should be able to basically switch or transform my centimeters to inches to figure out how to get through the door, if it would fit through the door. And the answer is yes. Yes, we can. Right. So the measurement of latent constructs does differ. So how does this differ when we cannot observe the thing we're measuring when the construct is latent? Right? We still need something we can observe. In our cases, in most of what we talk about in this class, item responses. So responses to these questions right here. We'll call those items. And we need a method to map the response to a number, right? So the number that I'm talking about here, the output, is like I talk about the inches. Once I measure my desk with a measuring tape in inches, I get the size of the desk in inches, right? So we need a method to go and map what we've observed onto this continuum itself, right? So, for instance, picking strongly greater equals 5 is somewhat like that. It's very arbitrary, though, right? We also need a way to aggregate all the responses to evaluate to a value that represents that idea for a person. So unlike my physical example where I measured my desk with one measuring tape in inches, right? In what we do in latent variable models, we collect multiple responses on about a person. How do we put them together to get a trait, right? In the very beginning example, I said, we could add together our numbers. That's one way, the add stuff up model. Yeah, that is parallel items. There are other ways as well, too. What we're going to represent is that construct as a latent variable as a variable with a distribution in the Bayesian sense. And that distribution will help define its units as well, too, right? So we need a way of scoring people or classifying people. Then we need a way to ensure what we just did means what what it think it does, right? With a physical construct such as length or weight, sometimes the validity argument is lost because we all live in the real world, right? At least we all live, shouldn't assume all of us. Maybe all of us in this class. You've all met somebody who's a little bit out there. But we're all subject to the same gravity here on this planet, right? We all have the same physical rules, at least for what we generally talk about with our life. We can get into quantum whatever and multiverse theory and stuff that may change that. But here, for most of us, we all play by the same rules of the universe, right? So we don't need a lot of validity to it. When we talk about length, we all can understand, hey, is this a measure of length? Almost anything can be a measure of length, so long as it's accurate. For what we do, we need a way to describe whether or not what we're showing is a measure of the construct itself. If that measure actually means it. If we're measuring satisfaction of life, does that actually really reflect satisfaction with life? Or is it something else? So that's methods for validation are what we'll need as well, too. We also need to remember that the values that we estimate for the latent variable won't be perfectly reliable, and I'll put this into a Bayesian construct for you. Do you remember last class where we talked about the posterior distribution of the probability of rolling a 1? That posterior distribution, even with the very informative prior, still had error to it. It was all not centered around 1/6. It was potentially gave up some change to it. For us, our distribution for ability or our distribution for the latent trait will be a posterior distribution, right? We've updated our belief about what a person should be. So that posterior distribution itself sort of quantifies how much uncertainty we have about the latent variable itself. That's important because uncertainty in the posterior distribution, we define in psychometrics as the term of reliability. Or better yet, the term reliability from psychometrics really reflects how much error there is in the how wide the posterior standard deviation is in a latent variable model of the latent variables themselves. Latent variables with very, very small standard error, conditional standards of errors of measurement, are highly reliable. And the contrary is also true. Oh, so, and the other part of this is if you have a value, a latent variable that's not perfectly reliable, and you want to put that into a secondary analysis. Let's think of a way you'd want to do that. Here in education, a lot of times you'll say, let's take an entrance test like ACT, right? ACT. How good is the ACT at predicting first year freshman GPA in college? It's a standard question we'd want to ask. Kind of relates to validity a little bit, right? If the ACT should be valid for admitting to college, we should see some type of measure of relationship to first year GPA. That secondary analysis, though, if you just take the ACT score by itself and stick it in the secondary analysis, you've also got problems because you've neglected that error. Right? You need that post-error distribution or that conditional standard error of measurement to really do secondary analysis as well. In Bayesian, it's interesting because we're going to run a Markov chain and we're going to have sampled from the post-error distribution. So let's imagine we take 1,000 draws of a person's post-error distribution, right? That in itself describes the variability around that person. If we took those 1,000 draws and found a way to synthesize those and put them in a secondary analysis, we'd be okay. That problem of forgetting error would go away. And we can. All right, questions? Am I going too fast or too slow, or neither? How many of you say pace is good the way it is? Thank you for the feedback. I appreciate it. Okay, let's talk about measurement models. Right? A distinguishing feature of psychometric models is the second word. They are mathematical models themselves. We call these measurement models, right? A measurement model is this mathematical specification that provides the link between the latent variable, or variables, and the observed data. And we sort of thought a little bit about that when we talked about the types of models we'd use in this example. Right? We may have one ability or one latent variable representing satisfaction with life, but here we may need a categorical outcome distribution to model how someone with that ability would predict or would answer this question itself. So that is the link that we're talking about. A measurement model always contains the data and the thing the latent variable it purports to measure itself. Now the form of these models looks very different across the wide classes of measurement models themselves, right? So you may have taken the factor analysis class and seen what a CFA model looks like, confirmatory factor analysis model. And you may have taken an IRT class and saw what an item response theory model looks like. And they don't normally look the same, but there's quite a bit of generality and overlap between them, right? So here's what measurement models need. They need distributional assumptions about the data, right? Here, we assumed a categorical distribution. In the terminology of generalized linear models, those distributions, like every statistical distribution has a set of parameters that describe it. In the sense of the data models themselves, the measurement models, they typically require something called the link function, right? Think of it this way. Let's take a look at this two-choice binary item here. The conditions of my life are excellent. The model for this is a Bernoulli variable, very much like rolling a 1 on the die itself, right? So there's a probability associated with picking yes, right? But that probability ranges between 0 and 1, whereas our latent variable itself is likely to be unbounded, right? Ranging between negative infinity and positive infinity, basically the way we think about it. So we need a mapping of the space of the real number line onto the space of 0 to 1 to make this model work. That's what's called a link function. A link function takes a parameter or a feature of a distribution and maps it onto an unbounded space, a number line in this case. We also need a linear or nonlinear form that predicts the data from the trait itself, right? So now we have a link function to transform a feature of the distribution we can go and put something that looks like a linear model in to predict it. The key here for all of this is that observed variables are being predicted by latent variables. And this is exactly the setup I mentioned before. If you could observe mathability and observe a bunch of test items, you'd use logistic regression already to understand how mathability maps onto test items. Cool? Yes, Vladimir. Yeah, I mean, basically, if you're specifying so the question is, what's an example of a nonlinear form? Yeah, absolutely. Nonlinear factor analysis exists. I'll just say that. Meaning, you could have some nonlinear relationship between a latent variable and your out to observe data. So, for instance, maybe, and I don't know why, but it's hard to speculate, but maybe there is a quadratic relationship between a person's factor score and the way that they answer this item right here, something along those lines. So the same way that we would put a nonlinear form into a linear model, right? We might exponentiate part of it, or we might take a quadratic term and put it in the analysis itself. We could still build that model into a latent variable model. Now, you make a very good point, Vladimir, in that almost every model in class from now on is going to be a linear function. So the latent variable itself has a linear function, like basically a linear or multiple regression without having that. But it's possible. It is absolutely possible. The other part, actually, let me just step one last other part where it could happen. If you have an item that measures two traits, right? Let's say you have a word problem in math. You got a person has to read a paragraph and then make a math decision about it, right? I would argue that that item is in part measures mathematics, but also in part measures reading comprehension, right? So now you have two traits for it. If you have an interaction of those traits predicting the item response, that's a nonlinear form as well too. Right? The interaction between mathability and reading comprehension to produce the item response would also be nonlinear. Does that answer your question? You're welcome. Yeah, so that's where I'm thinking about it. Most of the time, I think probably the closest nonlinear version will be that latent variable interaction. You don't see them much in the diagnostic model field, which is where I, again, got my start. That was the key. That was what we used. Now I've completely lost my presentation. So, yeah, most of them will be linear. Pardon me for losing where I was at. Other questions while I, figure this out. There we go. All right, moving forward then. Measurement models versus other measurement techniques. All right, so measurement models are a way of thinking about psychometrics than what most people without psychometric training do. So just remember that. If you weren't in psychometrics, if you're in engineering or in business or somewhere else, what would you do? Well, a lot of the world will enumerate a score for each response. A correct response is a 1, an incorrect response is a 0. Or option, in our Likert item, 1, 2, 3, 4, 5 for strongly disagree to strongly agree. All right? And then they will form a latent trait estimate by summing the scores all together. Lisa calls this the add stuff up model. I'll use the asterisk to describe what stuff means in her case. I will not use that word. At least not here. I use that word a lot. Anyway, as it turns out, the naive adding together of item scores actually implies a measurement model called the parallel items model. And you can show this in item response theory as well, too. Basically, the idea is this. Even with binary items, right? So you have 5 math items, yes, no, or correct, incorrect, right? The score from that is equivalent to a latent variable estimate, or it's correlation of 1 with a latent variable model from a confirmatory factor analysis, not treating the data as discrete, where the loadings and unique variances are set to be equal to each other. Loadings are all equal, unique variances are all equal. Basically, 2 parameters that are the key in the model itself. So yes. All right. Let's get into some characteristics of latent variables. Clearly, this class will span 2 periods, 2 classes. This lecture will span 2 classes. So we'll just do a little bit more here and we'll stop for today. But let's talk about this. Hypothetically, latent variables can have different levels of measurement. So what do I mean by levels of measurement? This is intro statistics stuff. We talk about interval level of measurement, right? Is an idea being we don't have a fixed 0 point, right? We don't have like height. We don't have a 0 height, right? But we do know that 1 unit difference is 1 unit across the entire scale, right? The interval is always constant. So if I have a score of 2 and Vladimir has a score of 1, that distance is the same between someone with a score of 3 and my 2, 1 unit apart. That's a continuous measure, right? I just said that. Wow, it's like I made these slides. Anyway, sorry, that's my own cue to myself saying, come on, Templin, get your stuff together. An ordinal level of measurement, something that we would define in diagnostic classification models, is where we can rank order people, but not determine how far apart they might be. So for instance, someone who we define as a master of a subject, and I say that looking at Sergio, master of a subject, that's a charged word in our language these days, is has more ability than someone who's not a master. But maybe we don't know how much more ability that happens to be. A student who's classified as proficient on their end of grade test in education has more ability than a student classified as, not yet proficient. But how much more ability is not defined. So that's an ordinal level. Okay, there we go. And then finally, you could even have a nominal level, right? And this case is in a general latent class or finite mixture where you're trying to classify people into groups. The groups themselves may have no metrical relation at all. It's just group 1, group 2, group 3. And I would call that a categorical model itself, right? Groups, classes, or clusters of people. No scale. So latent variables can have all 3. Often we teach factor analysis item response theory, but I will say each of these is a latent variable framework, and each of these frameworks fits into Bayesian, and I'll actually have examples of all 3 of these. Maybe not this full latent class model later on, because the full latent class model is a pain to work and stand. But on that note, I'm going to stop the lecture for today. Do you have any questions for me? Because we are out of time. Do you have any questions for me before we go for today? No questions. Hey, look at that. We have 15 seconds left, and I'm not going to keep you longer than I have to. All right. Well, you know where to find me. I have office hours tomorrow morning from 10 to noon. You know where to find my email. If you have questions, don't forget homework 1 is out, and I will leave you for today. Thanks for being here. Thanks for attending, and thanks for participating. Have a great rest of your Tuesday. Take care.